In this example, we have again a Brayton cycle. Air enters the compressor of an ideal air standard Brayton cycle at 100 kilopascal pressure and 300 Kelvin temperature with a volumetric flow rate of 5 meter cubed per second. The compressor pressure ratio is also given, which is equal to 10. The turbine inlet temperature is also given, which is 1400 Kelvin. So we have this information for the cycle. Then we need to determine the thermal efficiency of the cycle. The back work ratio actually, or the fraction of the work uh, from turbine which is given back to the compressor. And also finally in part C we need to determine the net power developed in uh, uh, based on kilowatt actually. So let's see how we can find the answer for these three parts of the question. As I said before, you need to know the cycle. TS diagram of the Brayton cycle, state 1, state 2, state 3, state 4. So you need to draw the schematic by yourself to be able to answer to the question actually. The information also is given, is shown on this TS diagram. The T1 is given 300 Kelvin. It is mentioned that the temperature and pressure at the entrance of the compressor. It means that the state 1 temperature is 300 Kelvin and pressure is 100 kilopascal. And you know that in a Brayton cycle, for this process from state 4 to state 1, we have a constant pressure process. So pressure for state 4 also is given when we have pressure for state 1. And also, it is mentioned that the compressor pressure ratio is 10. In other words, the pressure which we have here in state 1 will be multiplied by 10 for state 2. You know, here we have compressor, then air will compress during this process. Pressure initially is 100 kilopascal. It will increase by 10 times actually, times to this 100 kilopascal. So the pressure here P2 is equal 10 power 10 times P1. P1 is 100 kilopascal times 10, 1000 kilopascal. So pressure at the state 2 is 1000 kilopascal. Again, you know, for the process which we have from state 2 to state 3 for a Brayton cycle is a constant pressure process. So pressure in the state 3 also, which is after a heat exchanger or before turbine actually, is 1000 kilopascal. So we have pressure for all of these states. We have temperature for state 1 and temperature at the turbine inlet also is given. Temperature at turbine inlet mean temperature at the state 3, which is 1400 Kelvin is given. So we have this temperature as well. Pressures, temperatures, and also you know for the Brayton cycle that we have this configuration actually, this component. We have compressor, we have turbine, we have heat exchanger to heat gain, and we have heat exchanger to heat rejection. The total work output, the power output of the cycle is W dot, and the thermal energy which is given to the cycle is Q dot in, and the uh, uh, heat which is rejected to the surrounding actually is Q dot out for the cycle. And P2 to P1 also, as I said, it is equal to 10, P3 1400 Kelvin, P1 and T1 also is given. This is just illustration of what is mentioned in the question instruction. Now we need to determine thermal efficiency, back work ratio, and net power developed in kilowatt actually. So first, let's start with the assumption. The assumption which we have here, similar to previous example, steady operating condition exists. The air standard assumptions are applicable. Kinetic and potential energy changes are negligible, and air also is an ideal gas with variable specific heat. I already discussed about this assumption in previous example. To find answer for part A, which is the thermal efficiency of the cycle, we have this equation. If you remember, thermal efficiency of Brayton cycle without the regenerator and so on, we have the general equation actually for all type of gas power cycle, which is equal to the W net divided by Q into the system. But the W net and Q in is actually the amount of work, the network output, and the the amount of thermal energy which is given to the cycle. But what we have here actually is based on unit mass actually, Q dot in, Q dot out, and here W dot of the cycle. In other words, what we have here actually is W dot net divided by M dot. Then this will be equal to W net divided by Q dot in divided by M dot. Why we have M dot? Because the mass flow rate is constant through whole cycle. And W net actually for this cycle, for Brayton cycle, is equal to W net is equal to W out turbine minus W out W in actually for compressor we have W in. So let me just read this. So for the compressor we have W in C, and for W, this is actually W out of turbine, which means it will be equal to W dot of turbine divided by M dot, and W dot compressor minus W dot compressor divided by M dot, and similarly Q in, which is Q dot in divided by M dot. So we have this equation. Now we know also the W out and Q out in this cycle. Actually, here we have WT out, or the work output of the cycle, and here we have W in of compressor. So how we can calculate WT out or W in C for the compressor? We can calculate this if we write the energy balance equation for this cycle. In other words, if you notice here, W in will be equal to H2 enthalpy. This is based on the energy balance equation minus H1. WT out here, because this is out actually, then it will be equal to H3 minus H4. So this is actually what we have written here. Here, you know, the total efficiency is equal to, as I wrote here, W net divided by Q in. It is equal to W out for W turbine minus W compressor divided by Q in. WT, WC, and Q in based on the unit mass actually can be written like this. And this is WT actually. W dot T divided by M dot is WT. WT is equal to H3 minus H4. W dot C divided by M dot is WC, which is equal to H2 minus H1. I show you here. So simply we can substitute here H3 minus H4 minus H2 minus H1. How about Q in? If you notice here, we have Q dot in divided by M dot will leave us Q in actually, not Q dot will be Q, not Q dot. So Q dot in divided by M dot will be Q in. So Q in here, if you notice, Q in is in this process. And during this process, if we write energy balance equation, which I think you already have seen in many explanation about different type of the cycle for this chapter, if we write energy balance equation for this process, and if we use these assumptions, then the Q in will be equal to H3 minus H2. This is what we have written here actually. So H3 minus H4, H2 minus H1, H3 minus H2. We need to have enthalpies for all of the four states which we have in the cycle to be able to calculate thermal efficiency in this cycle. So now is the process which I think you already know how to do that. We need to find the properties for each state. For state 1, we have temperature and pressure. So simply for state 1, we can go to the table A17 for this temperature, 300 Kelvin, find enthalpy, H1. And also we can read PR1 or relative pressure for this state from table A17 by interpolation or directly. I think we have directly this enthalpy and PR for this temperature. After we find this, again here we have isentropic process, so we can use this isentropic equation, PR2 equal to P2 divided by P1, PR1. We have P2 divided by P1, 10. PR1 we have here, then we can calculate PR2. So we have PR2 property for state 2. We can go to the table A70 again, and by this PR2 by interpolation we can find enthalpy for this state as well. So we have enthalpy for state 2 as well, H1 and H2. Now let's see how we can find H3. In state 3, again temperature is given 1400 Kelvin. Simply we can go to the table A17 and find the H3 for this temperature, which will be equal to 1550.4 kilojoule per kilogram. So with this temperature, for this temperature, we go to the table A70 and find this enthalpy. How about state 4? For state 4, we need to use information which we have from state 3 and the process which we have from state 3 to state 4. Process is isentropic, and we can write this isentropic equation. PR4 is equal to PR3 times P4 divided by P3. But we don't have PR3, but as I said, we have temperature for state 3. Then we can go to table A17 again and find PR3 for this state by interpolation. So we have PR3 here to put in this equation. How about P4 divided by P3? Again, if you notice here, P4, we have the pressure for that. P3, we have pressure for that. If you remember, we have constant pressure processes here. So we have P4, we have P3. P3 is 1000, P4 is 100. Simply P4 divided by P3 is 1 divided by 10. PR3 here we have found in the table A17. We can calculate PR4. Now for state 4 we have a thermodynamic property. So we can go to the table A17 again and use this PR4. By interpolation we can calculate H4 or enthalpy for state 4 actually. So now we have enthalpies for all of the states. So simply we can use this equation. We can use this equation. We have H1, H2, H3, H4, and we can use this equation to calculate thermal efficiency for this cycle based on the enthalpies which we have here, which will be equal to 45.7%. In part B of the question, the back work ratio need to be calculated. Back work ratio or BWR is equal to the fraction of the work which is given to the compressor or WC in divided by W which is produced or W output of the turbine actually. And as I said, based on the mass unit, we can write W dot C divided by M dot, W dot T divided by M dot, or WC in actually, or WT out. We have already seen here how we can find that. H2 minus H1 is WC. H3 minus H4 is W turbine. H2 minus H1 divided by H3 minus H4. So we have these H or enthalpies, and we can put here and calculate back work ratio, which will be equal to 39.6%. Simply, you can see here almost 40% of the work which is produced in the turbine is consumed by the compressor itself. So you can see how much is effective the actually the efficiency of the compressor. As much as compressor need lower work input, the total efficiency of the cycle will be higher. And in part C of the question, we need to calculate the net power which is developed during this cycle. To calculate that, we need to actually find W dot of cycle, the work output of the cycle. Simply, you know that to find this actually, W dot of cycle is equal to M dot times W net of the cycle actually. The W net which we can get from the cycle, as I show in previous slide, W net is W turbine minus W compressor. So the H3 minus H4 and H2 minus H1. We have enthalpies. We need only to know how much is M dot or mass flow rate in this cycle. But what is given to us actually is not mass flow rate. It is volumetric flow rate, which is 5 meter cubed per second. So we don't have mass flow rate. We have volumetric flow rate. How we can find the mass flow rate by the volumetric flow rate? Simply we can use this equation. M dot equal to volumetric flow rate divided by a specific volume. But as you know, specific volume for each state is different from the other state. So the volumetric flow rate for state 1 divided by specific volume at state 1 or V1. V1 or a specific volume at state 1 actually can be calculated by this equation, which is based on the molar form of the ideal gas law from thermodynamic chapter 3. If you remember, V1 or the specific volume is equal to R specific gas constant, which is equal to 8.314 kilojoule per kilomole Kelvin, or 8,300 Newton meter per Kelvin, and molar mass of the substance, which is air here actually, and the average molar mass of dry air. You can find this from these tables actually. The molar mass actually for the dry air or for air is given 28.97. From table A1 you can find molar mass of the dry air. So we have M, we have R, and we have also temperature and pressure for state 1. So we can use this equation simply to calculate V1 or specific volume at state 1. So we substitute this in our equation, AV or volumetric flow rate. Then instead of V1, we just substitute this there. Finally, this equation will be our equation to calculate m dot. The volumetric flow rate is given 5 meter cubed per second. Pressure at the state 1 is actually 100 kilopascal or 100,000 Newton per meter square, divided by R. As I said here, we have R. The M or molar mass of the dry air also from the table A1 we have. So these are properties actually which we have here come from table A1. So we substitute here R, M, and T1 also was given 300 Kelvin for state 1. All of these are about state 1. And m dot will be equal to, based on this calculation, will be equal to 5.807 kilogram per second. And I just remind you, because here we have a closed system, we have a cycle for a closed system actually, then m dot in whole cycle will be same. V or the even the specific volume is different for different states, but the mass is constant, or mass flow rate is constant in all of the states. So now we have m dot. Substitute, we can substitute in this equation. We have enthalpies, and we can calculate the power, the net power output or developed actually in this cycle. M dot 5.8, and this is H3 minus H4, or W or work output of the turbine minus work input of the compressor. Just substitute, and we use this unity conversion ratio actually because it was mentioned that we need to calculate the net power based on the kilowatt unit for the power, which will be equal to 2,481 kilowatt, the power output, the net power output of this cycle actually. By this example, we reach end of this chapter, and I hope you have already learned all of the relevant information for this chapter.